my stream, and then I will drop that link in there for you. And then if Walter's here, can maybe drop that into the schedule. I would be most appreciative. Let me see, where are we at here? Okay. All right, there we go. All right, there's the link. How was spring break, everybody? How was anybody do anything cool for spring break? Stay in your bedroom? Anybody awake? I know we're out of the groove here on school. Cody, hot mic, unless you're intending to say something. Cody did more school. Excellent. Yeah, I kind of just tried to recoup, just tried to just keep resting post-surgical crapola. And I think I'm getting better, slowly, you know, off all the pain meds anyway. So that's good. It only took me a freaking month and a half. But okay. All right. We're rocking and rolling. So, damn it, Gabe, I'm sorry, man. Sorry. Really, truly. Yeah. Okay. So it's all very quiet today. It's too quiet. Let me tell you what's going down now. We're ready. So, but no, welcome back. I think, what's my math doing here? Do we have like 6 weeks left in the semester? Let me double check this because I like to, let me see. Today's Tuesday, the 16th. We got 1, 2, 3, 4, 5, 6, 7. 7 weeks. Thank you, Walter, for posting the link. 7 weeks. We can do this. We can do it. We can do it. I'm just kind of hoping, that that the pain just keeps dropping so I can just get my energy back. You know what I mean? Because there's been a little bit. In fact, I'm looking back now. I got to go back and rewatch maybe some of the lecture videos from like 4 weeks ago. Because I don't know what I said. I don't remember much about those weeks. So I'm elusively unaccountable for whatever I did while under the influence of narcotics during that early stage when we first got class back in the gig. So, and I'm also incredibly accountable for whatever happens right now because I'm totally lucid. In other words, this is like as good as it gets. You know what I mean? Yeah. Sorry. True. Okay. Today, here's the deal. Here's the deal. Again, I'm going to pull up the schedule just to refresh on where we are, which means I got to do the little dumb login factor. I also want to just calibrate, kind of, this is also sort of for me and Walter and Zach as well, to just calibrate where we are on the overall schedule. The class schedule is, it articulates a kind of temporal flow, meaning the order in which things have a tendency to happen. But it is not, in the strictest sense, like the calendar to which we must adhere, if that makes sense. Just out of curiosity, I don't know how bad it is right now. Wait, are we ahead? Oh, I don't have spring break in here.
No, spring break's in there. I've been moving everything down the list
Oh,
We've
it's
gotten slightly
March. Oh,
behind.
it's freaking March. Okay, hang tight. Yeah, okay, thanks, Walter. Uh, yeah. Okay, so yeah, we're behind. No, we're all right on time. Okay, sanity check me here, Walter. We're on time, right?
We Well, kind of. We had an open week at the very end of the semester with nothing in there. As things have taken a little bit longer, I've been shifting everything down
Okay,
on the
gotcha,
dates.
gotcha.
There
So,
used to be a full open week.
okay, all right. So you have done some sleight of hand. Yeah. Okay. Well, and we'll also probably, yeah, maybe do there. I don't know if there's some more shifty here or whatever. But in any case, what usually happens, everybody, is that some of these topics, like the stack is like 1 day. I think that's my recollection, Walter. I think it was like a less than a day. These topics here, they really do, the modules get smaller, okay? And sometimes that creates the emotion like everything's sped up. Well, the delivery of content is not speeding up. But some of these earlier ones, they come in, unless I granularize the modules better, which I could try to do, they're just bigger, beefier modules, but the delivery, there's just more in them. We get down the stretch, and module 9 is a day, maybe two. You know, I know 12 is less than a day or less, pretty much. So it definitely will. Um, it'll feel like it speeds up because the modules get smaller. They're more modules, but content is going to be the same. But here's the key pivot. Okay, we've been talking all up to this point, starting off with, all the way down to bits, right? And the idea of data and the idea of how you just do stuff with bits, and then how we do these circuits and how we, create these logic structures, right? From digital circuits. And we've been kind of just like building this thing. And we ended the last lecture, which is the digital logic structures, with a picture of the LC3 architecture at a hardware level. Okay. What we're going to do now as we launch into the von Neumann architecture. Um, oh, and by the way, Walter, I also now realize that this is like module 5. There's module 6. There's no way we do this lecture in 1 day. So I see now wherever you speak. Yeah, so we're a little bit behind, but it does work out. It does work out down the stretch. We're going to talk about the von Neumann model, the von Neumann architecture, which deals with kind of what are these different chunks that are in that big picture? How do they fit together in sort of, computer architectures? And that is going to get us into this idea of computer programs in an architecture like this. We will begin to actually do um, instructions, machine instructions. And that's going to be your first kind of intro into programming, actually programming in binary, believe it or not. And that's going to set you up by the time we get here to modules 7 and 8, where 8, we're going to introduce assembly language, which is this sort of higher level view of the exact same lower level things. So we're going to show you machine instructions, and then we're going to show you this like little easier way of doing those machine instructions that we call assembly language. Okay, that's just kind of to give you a sense of where we're going. But this is a little bit of a pivot from really hardware, really low level hardware stuff, to now we are going to today talk about getting this computer, the von Neumann architecture, and then the LC3, as a simulated computer architecture. And then we're going to be ready to say, well, how do we get this thing to do things for us so we can get Fortnite, so we can get Spotify? And that's where we're going. Cool. Just hopefully give you a little bit of a sense, of setting some expectations. Okay. But let's go. Let's do this thing. Nope, blew past it. John von Neumann, called the father of modern computing. Um, von Neumann was amazing. There were a lot of people in different ways and different places and different parts and different things. Von Neumann really gets kind of credit and gets his name attached because he wrote a paper, um, which I think I talked about with you. Didn't I? We talked about it. I think I dropped the paper in the link in the a PDF into the channel if I remember correctly. I was on powerful narcotics when that happened, but I seem to remember doing that. And there is in fact some debate about like who really sort of invented, who was really gets credit. But in any case, von Neumann is the one that we attach the name to. This guy was like this crazy prodigy, age 8, differential and integral calculus. I mean, I had those classes and I still can't do it. You know what I mean? He founded the field of game theory, etc. So anyway, this is our guy that gets kind of credit, but he was absurdly brilliant in a lot of different areas, of study. All of them very mathy, if you haven't noticed, math, physics, econ, stats. Uh, Ancient Greek, I don't know quite I don't know much about how that fits in. Who he was talking to in ancient Greek. I don't know. I don't know. But this is the idea. Okay. Now there really are kind of two. When I think of the von Neumann architecture, I think of actually two ideas. One of them is this idea of a computer architecture. Um, One of that is sorry, cold packs are going in. Cold packs being deployed. Oh, yeah. Okay. Um, One of them is this idea that you've got this machine that has a central processing unit, which has really two ideas inside of it: the ability to control the entire computer through circuitry, and the ability to do various kinds of math. A separate notion of memory, which we've been through. We built our own little memory. And then the notion of sort of like peripheral devices that you can take input from or do output to, right? This little idea right here is really the gist of it. And I know that you're probably looking at this going, well, yeah, but coming from this perspective right now, nearly 100 years later, of course it seems obvious. If you don't know what it is you're building, though, you understand how conceptually difficult that would be to just roll from scratch. Um, you know what I mean? It's non-trivial when everything's obvious after the fact, but when it's before the fact, you know, could you have come up with it? Well, that's the struggle. Yeah, Alchie, we can take tests multiple times. Yep, 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 yep. The only limit is once a week per module. So you can take like modules 1 through 12 every week. I don't see that happening, but it's possible. That's the only limitation. Walter, thanks. You already said correct. I'm way behind the curve by at least a minute. Okay. Um, Alrighty. So we're going to talk about basic components. Let's do it. What I'm going to do is just basically on this pass, we're going to take this picture and just talk a little bit more about each one of these little pieces. Okay. And then we will try to bring it together. Okay. So, memory. We talked about this quite a bit, did we not? Um, sure seems like we did. And we sometimes call this RAM. RAM is an acronym, stands for Random Access Memory. Really, we usually say RAM. The truth is that all of the various memory in a modern computer, this phone, this laptop is RAM. But when we talk about RAM and we refer to how much RAM, we're really referring to main memory. There's other memory. There's little chunks of memory all over the place that are doing different things. And technically, they are random access memory also. Uh, Not always, but for the most part. But when we say RAM, we're talking about main memory, okay, in your computer. We call it random access because you can read anywhere at any time, right? Remember that? Remember our little 12-bit, 4 byte, 3 bits per byte, little memory that we built. By setting that decoder, we could just turn on any one spot and pull that stuff out. That's the idea. So, you know, uh, hard disks. Now we're talking about if we talk about hard disks, not solid state, which is usually, some kind of like flash memory or some kind of, very, very fast random access memory. Traditional hard drives have this platter that spins, right? So it's random in the sense it's not, well, it's not. It's random in the sense that I can go to different spots, and that's why when you uh so Josh, you're gonna have to, oh, let me see. I don't know what that interaction is, Walter and Josh. Um, but when you have what's an example? Sequential memory is something like an old VCR tape, right? Where you have to rewind the tape, right? You're playing and you have to like fast forward to get to some spot, then you go and you know what I mean? Everything is in sequence. You can't just like instantly just pick that spot, this spot, that spot. The memory that we designed, that we looked at, you could just by setting a bit pattern to identify the address, right? That would just turn on that location. And because of the circuitry, that's the that's the byte or the part of memory that would drop back out. Okay. That's really, really random, truly random in the sense that I can go anywhere at any time. Anything that has an element of sequential factor is not strictly speaking random. If I have a movie file, right, or an MP3 or something like that, I can it can play sequentially, but it's still I can just like grab the little thing and just slide it to anywhere and be boink at that spot. Boink is the sound that it makes. I can be right at that spot. Um, but in the old hard drives, the platter would actually spin, okay, going like that, and then there was this read write head. I'm just looking around like I need like a paper plate or something. Um, anyway, I don't know if I have anything suitable. A 3x5 card. 3x5. Picture that this is a spinning platter. Then a read write head would come in over the top, and that read write head would identify a particular track, right? And then the thing has to spin. You have to wait. Oh, here comes the sector I'm looking for. You got to get this in position this way, then wait for the disk to pass under the read write head while I read the bytes and stream them in, but I'm still not like able to go to a specific, byte in memory on that disk. I can go to a specific, you know what I mean? There's latency, there's sequential components to that whole thing. So it's a little random, but not entirely, not fully. That was an amazing graphic demo. I'm really proud of myself. Okay, all right. Please drop any questions you got. It's all good. I'm going to keep going. So here's the idea of memories. We did that little tiny one. This is trying to blow that idea up a little bit more. Memory really does look and kind of not look like, but kind of act like functions like, like the post office, like check these boxes out, 207, 208, 209, right? 212, 213. And each one of these is a location in memory. That's the address right there. So there's your address. In this case, this is an eight byte memory. Okay. And so being 8 bytes or having 8 locations, each one holding a byte. That's the configuration here. Well, then we need how many bits for the address? three. We need 3 bits for the address because that allows me to identify 8 different values. From 0 to 7, those are the addresses. Boom, there they are, right there. And that's the address. And then these are the contents, the stuff that's in at that address. You got to be able to differentiate and understand, how that sort of, that differentiation, right? It's a little bit of a kind of a conceptual, a conceptual fragmentation. That little jump is difficult sometimes for some people, but so just be aware of that. Now, a couple of key terms here when we talk about memory, we talked about the address. So this is a number, right? It's an unsigned integer. Real quick, then if you want to drop comments here, why is it an unsigned integer? Why is this not a 2's complement integer, right? This integer is represented in unsigned integer sort of notation, okay? Treated as an unsigned integer. It's not treated as a 2's complement number, AKA an integer in 2's complement notation. Why? Why? And I can even, if somebody wants to jump in on the voice part of chat, that's cool. And if not, just drop it in the comments. But the address is just a bit pattern that identifies a location, just like we've been through. Okay. Yeah, Cody, no need for negatives. There's no negative numbers. 2's complement notation allows for, right, positive and negative numbers to be represented. Unsigned integers, there are no negative numbers. All the numbers start at 0 and they go all the way up to all the bits are on, right? So in unsigned integer notation, the smallest number is 0 and the largest number is all the ones are on, okay? That's not the case in 2's complement notation. Yeah, there's no negative street addresses. You do get a little bit like, something, something north and something, something south, but they're still positive. You know what I mean? They're still positive numbers, but that north-south is a little bit, I don't know, in like street addresses. Okay, the address space. So these are terms that you kind of need to commit to memory. Address by now should be pretty clear. Address space has to do with how many unique locations, how many mailboxes, okay? How many houses on the street or how many unique addresses on the street. And then this becomes a really important idea again. If I have 2 to the n memory locations, I need n bits in my address. That's just what we walked through. It's what we walked through right there. Actually, yeah, right there. Okay. There are 8 locations. I need 3 bits for the address. Okay. If I've got, I don't even know, right? If I've got 64 gig of RAM, then, we walked through that before, didn't we? Or do I have that coming up? No, we walked through it. We walked through it already. How to pull that, value back out of there. And then, so that's the address space. How many addresses are there? Okay. How many locations there are? The addressability, and I really apologize, it's like address space, addressability, they all say address. So it is a little bit arbitrary, in that respect, so I apologize. But addressability has to do with when I point to a particular spot, how many bits are in that spot? How much is it, how big is every mailbox, right? If I have apartment numbers in your apartment complex, for those of you that live in apartments, how many beds are there in the apartment, right? How many people live in that apartment, that kind of thing. So obviously in this case, it's got to be uniform across the computer, or across the random access memory, the main memory. Yeah, what's the data size? Okay. When we say that something is byte addressable, it means that at every location there is a single byte. Okay? In that case, the address space is also exactly the same as the amount of RAM. Make sense? If I tell you I've got 64 billion memory locations, 64 gig, locations, and then you're like, well, how many bits are at every location? And I'm like, 8, just 1 byte at every location. Okay, how much RAM do you have? 64 gig of RAM. 64 gig of locations, 64 gig, each location has one. What's 64 gig times one? 64 gig. So if I say that there are 2 bytes at every location, 16 bits, and I've got still 64 billion approximately, um, you know, locations, and you've got 2 bytes at every location, how much RAM do you have? Well, 64 billion, 64 gig of locations and times 2 bytes at every location. You got 128 gig of RAM because every spot has two, every single spot, and there's 64 billion spots. If it's not byte addressable, we call it word addressable. This is just the terminology, okay? We call it word addressable. And word addressable always means, well, yeah, I mean, word addressable means that you've got multiple bytes at each location. Almost always, the number of bytes at each location is a power of 2. It's 1, 2, 4, 8, something like that. Um, just because everything inside the computer is easier when stuff is just powers of 2, for all the reasons we've talked about. Okay? Everybody cool with that? For some reason, this is a bizarre stumbling block for some, where I'll be like, okay, you've got, you got 128 locations in memory, and every location in memory has 2 bytes in it. How many total bytes of RAM in the machine? And sometimes it's like 17. No! It's the first number I said times the second number I said. How many buckets? How much in each bucket? It's simple multiplication. Okay. But for some reason, there's like I don't know, like a conceptual thing. I'm just saying that if you're in that category, then you gotta pound through that and get your head around that. Okay. To overcome. Some of you, it's whatever. You're mathy enough that it's just like, no, obvious, got it. But if you're going to struggle, then you just got to spend the time. Talk to me, talk to Walter, talk to Zach. Mostly talk to Walter and Zach. I've been so unreliable in my recovery, but I'm coming back, baby. I'm coming back with a vengeance. Coming back with no vengeance. I'm coming back with kindness and no vengeance. Um, okay, memory. What else? Okay, now here's a couple of ideas, and we're going to show you how this all fits into the architecture. We'll break this down in much finer detail, but we're still kind of high level view. There are 2 registers. Now, a register is a small chunk of memory that's very special purpose. Okay? It's built to have a certain purpose. And we're going to talk about the memory address register and the memory data register. Okay? Here's the memory address register. It's an unsigned integer. Again, same reasons that we talked about, right? It's an unsigned integer. It is a little piece of memory where we put the address of whatever it is of the location in memory. It's the spot we're going to write to, or it's the spot we're going to read from. All right. You can view this address as a sequential number, right? Of the location in memory. It starts at 0 and just almost like counts, right? It's location 0, location 1, 2, 3, 4, going down to however much space you got. It's also can be viewed as a bit pattern, so that when we look at it from a hardware perspective, that bit pattern, because it's a bit pattern that feeds the lines of a decoder, enables one line in memory, one spot in memory, and turns all the others off. All right. Everybody cool with that? I'm going to come back to this last bullet real quick because I want to just show you this. When we did this picture, the famous picture, right, where this was 1 byte right there, that whole top, sorry that my little cursor is so small, but that top thing is 1 byte, right? In this case, it's 3 bits. But these two lines, that is the MAR. That conceptually is the memory address register. There's some piece of memory that you put the address into, that address enables, turns on and off certain lines. Kind of cool. That causes one of those bytes to be accessible and for all of the others to be blocked. And we already walked through this thing in great detail. The MAR has to have enough bits to address all of the locations. Okay, this is that right there again. Okay, there are 8 locations. I got to have 8 addresses. How many bits do I need to get 8 addresses? How many addresses do I need? I'm sorry, how many bits, right? How many bits do I need in my memory address register, my MAR? How many bits do I need if I had 1K? I'm just going to let anybody can just drop this in on the chat if you want, or just chime in on voice. Um, if I've got 1K of RAM, how many bits does my MAR have to be? First of all, what's 1K? What 1K is 1024, right? What is 1K as 2 to the what? 2 to the something. If you take 2 to the n, what is n? If the answer of 2 to the n is 1024, what is n? Now I wait. Yeah, thank you, Gomez. Thank you, Jace. 10, right? 2 to the 10th. And if you really want to do it, break it down use your hands. Use your hands. It's fine, you know? Um, anyway, 2 to the 10th is 1024. All right. So if I have 1K of memory, my MAR has to be 10 bits. Ta-da! And if I have a meg of memory, how many bits does my MAR have to be? Give you a hint. A meg is a K times a K. 2 to the 10th times 2 to the 10th. When you're adding powers. No, thank you, Gomez. Thank you, Gomez. Second Gomez. Yeah, no, 20. 2 to the 10th times 2 to the 10th is 2 to the 20th. When you've got powers, you take, if the base is the same, 2 to the n times 2 to the, pick another variable like m, then the answer is 2 to the n plus m. You can add those exponents. That's how that works. Yep. Okay. And then we already did the picture. Okay. The other important register that relates to memory is the memory data register. Okay. The MDR. The MDR has the value of what's going to be written into memory or receives the value that's coming out of memory. All right. What is the data? What is in there? What does it mean? What's the contents in that MDR? I don't know. I don't care. The MDR does not care. MAR cares. What's in the MAR is an address. It cares. What's in the MDR? Data. The program knows. The program cares. And how does the program know? Because the programmer knows. Programmer cares. But nobody else really. You can't tell, right? There's a question that always comes up. How do you tell whether how do you tell when a piece of data is, like, I don't, what it is, what it means, how do you know? And the answer is, well, just by looking at it? No way at all to know. Just by looking at it. No way. Uh, it means social contract. It means whatever the programmer decided it was going to mean. Is that value a pixel? You know, is the value an address? Could be an address of something else. Could be a little piece of a moment of sound in an MP3 file. It could be, it could be an instruction. It could be, it just doesn't, we don't care at this point. The hardware does not care. Whatever was in that location in memory, that's what's now in the MDR. Now, the second bullet is actually a really kind of key takeaway in terms, I mentioned that this overall architecture is one of the big deliverables in this idea of a von Neumann architecture, right? But one of the really big issues with the von Neumann architecture, is that the code and the data are they're just in memory. They're just contents of memory. Okay. Now that's a little bit of a funky idea, really, because back in the day, you would actually program the earliest computers, even the earliest digital computers. You would program them by grabbing cables, for example, and like plugging stuff in. Now that would program the computer, and now here comes the data coming through. Well, this was all of a sudden this idea that we've got this memory, and in the memory, there is both code and data. So when you look in memory, could be data, could be a program instruction, and you don't know just by looking at it. You don't know. You can't tell. We talked about how big an MAR had to be. How big does the MDR have to be? And this is a lot simpler. The MDR has to be whatever the addressability is. If I say it's 64-bit addressable, meaning that at every address there's 64 bits, then I've got to be able to take whatever's there and pull it out of there and put it into this register. Well, how big does the register have to be? 64, right? Whatever's there, pull out and put it in this register. It's just the same size of thing. It has to be the same size as a location in memory. Because, right, I'm going to take from that and put it into memory, so it needs to match. And when I pull it back out, it's got to match. So that's easy. That should be really, really trivial to remember. Okay? And in our old picture again, our cool picture point of reference, this up here where we showed you these data lines kind of coming in, and and remember at the time I said, don't worry about like, where's that coming from, whatever. Well, the reality is there's a little piece of memory up here called the MDR. And the reality is we've kind of like, this picture has MDR at the top and MDR at the bottom. In reality, it's the same register. Just like wrap this over to the side and make it the same thing. And then you run wires. This is conceptually simpler to talk about, but it is the same register, the same memory. Okay, I don't know if that helps or hurts. Anybody going mind blow on this at this point? Anybody blowing the head gasket a little bit? Are we okay? Because I'm going to keep going because I have to. Keep pounding. Remember, you don't fail unless you bail. That's just don't bail. Don't bail. Stay with me. Okay, that's it for memory. Okay. Okay, here comes the CPU. The central processing unit. This guy right there. This sort of bucket of logical guts. This is where actual information gets processed. So we talked about, and we kind of briefly hit these. This will go a little faster. The control unit is running everything, okay? Remember I showed you a picture. I know you remember this because it was so exciting. I showed you a picture of the state machine that's inside the LC3. Well, where's that state machine inside the LC3? The answer is in the control unit. Literally the circuitry that hardwires that state machine is inside the control unit. It's running everything. In some architectures, conceptually it'll be part of the CPU or not, but I view it as being fundamental to the idea of a CPU. And then the ALU, the arithmetical logic unit, also called the arithmetic slash logic unit, is basically just all the math functions. A lot of times when you get into like really math intensive stuff, you'll have things like floating point coprocessors and graphic coprocessors, stuff where they'll take a really hard problem and they'll just give it away to another processor so that the main CPU that you're running the whole program on isn't bound cranking to do a bunch of math, throws it over there. That's all customized to math. Gomez, you got hot mic, I think. You go over there to go do all this specialized math. It goes real fast. And then, in a shorter time for the CPU, than if the CPU tried to just do the whole thing, the answer will come popping back. Okay. And then there's local memory, which we call registers, which are just like fast little, close by kinds of memories. We do this all the time in our real life, right? Hey Gomez, you got a hot mic. Gomez, hot mic. Hang on a second. There we go. Dropped a little chat. Okay. Um, so we have sort of like I don't know, man. I don't know. But anyway, we do this all the time, right? You've got like your desktop space. We got like pockets that we put stuff in, right? We got file cabinets. We have, we have like big storage spaces, garage storage units. We do this in our real lives all the time, right? Imagine that every bit of everything you ever had in your life was in a storage unit, a mile away. Like, like the note you wrote to yourself on a Post-it note is actually in the storage unit. So every time you want to read the Post-it note, you got to drive to the storage unit. It would be dumb. So instead, you've got little Post-it notes, around your desk or whatever that you keep kind of close by. That's just faster, right? But there is a time and a place, um, for larger storage that just takes you a little more of a pain to go out and get to. All right. So that's it. That's all I want to say, really. So that's what else to say? This feels like, oh, that was the CPU. The CPU has the control unit, ALU, and the registers. Now we break those down. Here comes the control unit. This is the whole flow. All of the intelligence of the computer is in the control unit. Okay. And in particular, these become really important, and they will become more second nature to you. One is a program counter. Now, right now, this is a little bit of Trivial Pursuit, right? I'm going to say these things, and you're going to go, okay, I don't know what that is. Program counter is going to become really, really second nature to you, okay? Like really, really soon. It's a register. It is a register, little piece of memory. It holds the address of an instruction, okay? That's what the program counter is. And in particular, it holds the address of the next instruction you're going to read out of memory and then execute. What we haven't gotten yet to in the von Neumann architecture is the fetch, decode, execute cycle, which is, I think, a very, very powerful deliverable of in the von Neumann architecture. And we're going to break these down, I think, as well. We'll get to them before too long. The instruction register so the program counter points to a location in memory. When you pull that value out of memory, it goes into the instruction register. Okay, so that's the little register that hangs on to the stuff that came out of memory. That's the instruction. Then the control unit can look at that instruction, decipher it, figure out what to do, and then run it through the state machine and do whatever the next thing is to do. Okay, That's how the computer runs. This is a quick whirlwind tour. We're going to drill down more on these, but this is the quick tour. The ALU, basic stuff, add, subtract, logic operations, and or not, you know. Um, Typically, the ALU is going to operate on values that are the same size as the word length of the computer, meaning the size of a location in memory. If you got 32-bit words, ALU typically is going to be 32 bits. It'll take 32 bits. Doesn't have to work exactly like that, but that is common. And modern computers most commonly are 32-bit and 64-bit. Obviously, smaller and larger varieties exist. Okay. The other thing is that there are the local memories, the local registers that are close by to help with local storage. They can talk directly to the ALU. The ALU can talk directly to those registers, so it has very quick access to that local memory that you've got. Okay, I'm just going to keep going. Stop me if you have questions. Uh, then we have input devices, not super complex. Keyboard, my mouse, mic, right? We sometimes call them peripherals. That's it. Keyboard's the most fundamental input device, probably. That's it. And then output devices, the monitor, you know. When I show you the LC3, you're going to see that there's a little monitor, which is just like a text base. Text can just kind of come out, this is me, this is text going off the screen. That's not a bad impersonation, I think. But basically anything that goes out is is an output device. Okay. And there's a whole section down the stretch that we'll talk about that there are devices that do both input and output, like your hard drive, like network adapters, Ethernet, Wi-Fi, Bluetooth, any sort of data communications is sort of bidirectional. But we lump everything together and kind of just call all of it I/O. I/O devices, keyboard is an I/O device, your speaker is an I/O device, etc. Okay. Um, all right. Now, here's the book's view of the von Neumann architecture then. Okay. This is the book's view. There's memory. I don't like this view. There's memory. There's output. There's input. There's the control unit. Program counter. I'm still trying to figure out if that is deliberately trying to be a graphic of a human finger. Because I think so. I don't know. I don't know. And then this processing unit with the ALU and, you know, I think this temp, I think is meant to be like local memory. I don't like this view. So, yeah, I mean, I don't know. It's a view. This was our other view right there, right? For whatever it's worth. But the LC3, which we use in this class, is an example von Neumann machine. And if we did some other stuff, like if I can ever get off my butt and create a Raspberry Pi track or option for this class, that obviously the Raspberry Pi running this ARM64 processor is another von Neumann architecture. Okay, the big advantage to the LC3 is that it is relatively simple. It's not like the ARM spec. It's not 1,000 pages or 1,500 pages or 2,000 pages. It's big. Um, you know, and in fact, how simple is the LC3 architecture? Well, it's so simple that that's basically it. And if I showed you this same picture for an ARM processor, an ARM64, it's going to be a lot more complex. So the challenge is, and I've noodled over this quite a bit, uh, do we just, if I did a Raspberry Pi for everybody, it looks a little better on a resume for whatever that's worth to you, but there's a lot of crap that you really don't want to care about. And so you have to put blinders on all the time and like, I'm going to take this guided path through it, ignore everything else unless you're ready for it. That's why when conceptualizing having a track, where I would have some lectures on the instructions that were focused on the Raspberry Pi, others focused on the LC3, so that if you're not if you want to go down the Raspberry Pi track, you go down that track. And it's going to have a little bit of pros and cons educationally. LC3 has the disadvantage that there's no real computer that does this outside of like Minecraft or wherever somebody happens to have just built little simulators to do this stuff. But you can't go down to a store and buy an LC3 processor, and I don't think you would want to, frankly. But it's okay. It's not its purpose. Its purpose is to help with education. Okay. And it does that in part by simplifying everything really, really dramatically. And the other thing I can tell you, the first, the first assembly that I ever worked on, the first sort of low level machine language was a simulator for a virtual machine in a crap, what was it? It was like a prime mainframe, and it was 1982, 83, you know, and it was octal. All the stuff was octal. It wasn't even hex, which is 3-bit chunks of stuff, and it was odd and whatever, right? But later on, and then I think the next one I was really exposed to was probably 6502 assembly, which was the processor, the Motorola 6502 processor, was the processor in the Apple II. And so, I knew how to do assembly language on that thing. And then that had its own little weird quirks, like how to write to memory, how to write to the screen, for example, was a weird thing where the memory locations were interleaved every other one, and you had to do all this crazy math to be able to just write graphics to the screen. Um, and it was just to try to make the output on the screen smoother. That was all I was trying to do. So it was solving a certain problem. I mean, just saying that every time you get something real, there's a bunch of goofy trade-offs that are not ideal either. And then probably the next one I did was 8088, pronounced 8088 and spelled 8088, um, which was an 8-bit Intel processor. And then the next one I probably touched was 8086, which was a 16-bit Intel processor, spelled 8086, right? The addressing scheme in the 8086 assembly, well, I mean, in the hardware, in the low level, whatever, there were like, to get to it had a 20-bit, the default was there was a 20-bit address, right? So you had 2 to the 20th was the max memory you could build with that chip. Okay, so what is that, right? At a 20-bit addressing scheme, it's a 16-bit architecture, 20-bit addresses. So how much memory? And it was byte addressable, if my memory serves me. Was it byte addressable or was it 2 bytes? It might have been 2-byte words. I think it was 2-byte words. I think it was 16-bit at every location. So, okay, here we go. Um, so let's go. Let's go. I got 20-bit address, which is clunky, and there's 2 bytes at every address. How much memory was max? What was the biggest amount of memory you could put into that machine with an 8086 processor? What say you? There's 2 bytes, Gabe. 2 bytes. So on the right track, 2 to the 10th is a K, 2 to the 20th is a meg, but there's 2 bytes at every one of those memory locations. So how much actual RAM? How much actual memory? Boom. There we go. Exactly. Yeah, exactly. 2 meg of RAM was like the maximum amount of RAM you could put in this thing. Because you could go, I mean, if you stuffed more RAM in there, you couldn't address it. Okay. Now here's the other thing. How did you build that how did you build a 20-bit address when you have a 16-bit machine? And the answer is there was a there was actually there were code segments and there were data segments. That's the other thing, is the memory was partitioned. I'm just saying this was a very, very simplified, stripped down architecture. When I was touching it, it was 1988. And when you go for that, like all the way back, it was crazy complex. So to make that 20-bit address, you had to have a segment and an offset. So there was a segment register and an offset register, and they were each 16 bits. And then the segment, you had to they were offset by 4 bits, and then the values were actually added together, and that then became the address that you went out to memory to grab. And see what I'm just saying? Like, you could say LC3 stupid, so arbitrary. Well, you know what else is stupid and arbitrary? The 8086 and the 8088 and the 6502. And these were real products. You know what I mean? This was the IBM PC and the Apple II. These were revolutionary products, and it was back, and these are ancient past where everything was simple. So you want to go ARM 64? Well, it's just going to be complex. It's going to bring in a level of complexity. So the difficulty for me is trying to craft the course in such a way that you can navigate it but feel safe, because there's all this crap you don't need to know about. That's the bottom line. And I'll still do it, but I think I'll probably leave the option. But here's the other thing I want to say. For all the weird arbitrary crap, my experience is once you understand these kind of core ideas, even if you then have to go do assembly language in some other world, you're going to look at it and you're going to go, no, it's okay. I got it. Yeah. No, where are the registers? How many registers are there? What are they? What's the addressability? The skills are all going to kind of be there. They're all applicable. Okay. Okay. What we're going to do now, though, is we're going to take this here picture of the LC3, and we are going to break it down in the same way. Let's look at, yeah, so Bray, the question is, even with the Pico or the Zero, there's still a level of complexity, because I don't even know, uh, yeah, like there's still a processor in those, and that really is what's driving that. So fair enough, 32-bit, right? Um, this whole world is all 16-bit. So, but again, you're absolutely right. You're absolutely right. You can still go simpler on those architectures, but there's still going to be a bunch of arbitrary crap. That's kind of the bottom line. Even then, right? So can you make it more simple? Absolutely. You know, yeah, with those kinds of options. And maybe that's the way to go as well, or, you know, I don't know. I really don't know. Got to figure it out. Um, okay. All right, here's what we're gonna do. We're gonna break this thing down. We're going. There's memory. Remember memory? Remember memory? Oh, you know the strange thing, by the way, Walter, we're actually almost about halfway through this lecture. Um, I'm probably speeding up a little bit as well. So we might not be that far off. But anyway, let's talk about this. There's the memory right there. Um, and that's it. There's the MDR, there's the MAR, there's main memory. The lines and all the other crap, we don't care so much. Remember I talked about the bus as this big data line that everybody like taps onto and then, pull stuff off of or put stuff onto. Well, if I need to, write things out to memory, then I've got to push them like right here. See that little thing right here? Or where else do I write to memory? Um, that actually goes out, but I'm reading from memory. Oh, here comes instructions come in this way, etc. Oh, and then here we go. That's coming. Wait, is that coming from memory? No, no. Yeah. Anyway, bottom line, that's the data register. We'll break this down in much better, closer detail. There's some things that'll come a lot more clear later. Okay, so now we're talking about the particulars of the LC3. All right, the MAR is 16 bits. That means you've got 2 to the 16th memory locations. So how much RAM is that? By the way, MDR is 16 bits. The addressability is 16-bit addressability. There are 2 bytes at every location in memory, okay? And you've got 2 to the 16th memory locations because you've got 16 bits. Now, if all I told you was that the MAR is 16 bits and the MDR is 16 bits, if that's all I told you, and then I said how much RAM is in the LC3, you have the information you need to do it. You know there's 2 bytes at every location in memory. You know there are 2 to the 16th locations in memory. So how much RAM? Well, 2 to the 16th is 2 to the 10th times 2 to the 6th. 2 to the 10th is a K, 1024. And 2 to the 6th is a 64. So that's 64K of locations. But there's 2 bytes at every location. Boom, Gomez, 128K. 128K, that's it. That is a dink processor. Very, very tiny. Okay? Cool. But those are the particulars. MAR 16 bits, MDR 16 bits, everything's 16 bits. Very, very simple conceptually. Here comes I/O, which we're going to talk about in much greater detail later. In the LC3, we've got a keyboard and we've got a monitor. That's it for I/O. That's it. And we're going to break all this down later on. There's a data register and a status register for both the keyboard and the monitor, and what they do, we don't care about right now. We'll get to that. See the speed? You feel the speed? Feel the wind? Here's the processing unit right there. Now in the LC3, they kind of separate the processing unit from the control unit. Fine. You know what I mean? Some of these lines are a little bit arbitrary. You could say everything in pink is the CPU if you wanted to. Okay, there's processing unit. What do we want to say about it? Oh dear, what did I say? Dr. K's tired. There's an ALU, that's the math guy. There are 8 registers. This thing that says reg file to me it's technically correct. It's a little confusing if you haven't seen it before. Like a file? Yeah. Set of registers. You don't care. If you want to think about the registers as being locations in a file, fine. But you can also just think of them as 8 separate little registers and you don't care how they're organized. Totally fair. When the ALU does addition, it assumes that the numbers are 2's complement integers. Okay? It assumes that the numbers that it is doing math on, that it receives, like, hey, add these 2 numbers. It goes, okay, I'm assuming that these are numbers represented in 2's complement as 2's complement integers. That's its assumption. Okay? And we already talked about how to build that adder. We did that adder. You can do a bitwise AND. You can AND these, AND these values together and get a certain value. And you can knot them. And this is the crazy part. That's it. Now that is a remarkably stripped down instruction set. Let me just say that is exceptionally stripped down for an instruction set. Okay, really, really is. You could argue absurdly stripped down, and this to me is one of the big weaknesses of the LC3, where there's no tangible machine probably that you could buy today, CPU, even small embedded processors, that is going to be that stripped down. Okay. Now what that does though is it does give you an opportunity to strip your understanding down to a very low level as well. There's an advantage there, but just know that that's pretty small. There's the control unit over here. What are the big chunks? The finite state machine, very important, directs everything. And then every time the clock goes, that state machine just moves one more. It just turns the crank. Every time the clock hits, the state machine advances. And every time the state machine advances, stuff goes on, stuff goes off, and the machine grinds through and does what it does, which is kind of amazing. We talked about the instruction register, which is when we pull an instruction out of memory, a program out of memory. That's where it goes. And the program counter, which holds the address of the next instruction we're going to go get. Okay. Instruction register down here, IR. Program counter up here, PC. Again, the little, lots of this other little stuff don't care about for now. Back together. There it is. Okay, now, did we talk about fetch decode? We had to have talked about fetch decode execute cycle earlier, right? Or have we really not gotten to it yet? I just feel like I should have talked about it by now. Anyway, the idea, did anybody remember? I feel like we talked about it at least some. But fetch, decode, execute. The whole idea is I have this program counter that has an address in it. I go out to memory at that address. Like, okay, what's the address? 74. Okay, go out to 74. Grab the stuff, pull it out, put it in the instruction register, decode it. Like, okay, what are we supposed to do? Okay, we got our marching orders. Execute it. That's it. Fetch, get it, decode it. I know what to do. Execute it. Go. Do what it says. Repeat. That is all the processor does. That's it. And when you're done, you have Fortnite. That's amazing. Okay. Or if you're of my antiquity, you have Doom. Everything's been downhill since Doom. I just want to say that. Yeah, I know. Get off my lawn. Go ahead. Say it. Say it. Okay, Boomer. Yeah. Ever since Tetris, it's all been downhill. Okay, Quake. I don't know, man. I don't know, Trent. Okay. Here's how instruction processing goes. This is a really key idea, okay? Very, very key idea. The program and the data are all just bytes in memory. Okay? Oh, nice. Matthew. No, no. Sorry, I'm watching the GIF. I can't stop myself. Sorry, you got me with that one. Okay, do you understand how revolutionary this idea was, that the program and the data were just bytes in memory? Crazy. The program gets instructed one instruction at a time by the control unit. That's it, by the fetch, decode, execute cycle. Program counter says where to get it. What I pull out of there is an instruction, and I decode it. The control unit decodes it based upon the state machine, and then it executes it based upon the state machine. That's it. Okay, so we're breaking this down. Now we're going to drop back into a little more detail, and based on time, we got 5 minutes. We won't finish this lecture, but we will next time. And what is this? What module are we on? Is this module 6? Feels like it. No, 5. This is module 5. Okay. Yeah. So we're going to finish module 5 on Thursday, which means module 5 this week. Keep playing bingo and get this thing cranked by the weekend, okay? So the computer instruction, the most basic unit, yeah, but it's actually like we used to call atoms, atomic atoms because they couldn't be separated. Then we came up with protons and neutrons and croutons and all the other tons, and then we had to break those up, and you know what I mean? It's like, I don't know. A little bit like that with instructions, right? You got this notion of here's an instruction, but it turns out it is like divisible, much like a proton or a crouton. Philosophical question. If you take a crouton and you break it in half, do you have a half a crouton or do you have do you have two halves or do you have two croutons? I'm bothered by that. Any ideas you have are going to be really appreciated to help me through my existential crisis that I'm having here on that small matter. Um, Trent, you are correct. That's good. That's good. A lasagna on top of a lasagna is still one lasagna. It just got bigger, is all. Um, Somebody look up Taco Town. It was an SNL skit from the antiquities. Well, not the ancient antiquities. Taco Town. Somebody find it. Drop a post, please. Do a public service. Tacos. Now that's what I call a pizza. Um, I think you'll like it. I think it'll be worth it to everybody. And we got 3 minutes left. Okay, here we go. Back on task. Taco Town. Thank you. Is that playable? There we go. There we go. Yeah. Don't give me 3 minutes to before you watch it though. Give me 2 minutes. Nah, you know what? My butt hurts. You know what I mean? Everything hurts in my body. So I'm just going to talk a little bit about this and we're done. And I got to go like stand up. That's the worst part. To rest, I have to stand up and walk. It's brutal recovery, my friends. Okay, here's the deal. That's an instruction. And I know I've lost all of you to Taco Town. And that's on me. I have only myself to blame. So you know what? Uh, I just want to say this. Every instruction is 16 bits. That's one thing I want to say. There's an opcode at the beginning. We're going to come back to it. It's 4 bits. That's the second thing I want to say. And the third thing I want to say is taco. Now that's what I call a pizza. Taco Town. Yeah. And it was all inspired by whoever the crap brought up the dumb. That was Trent. Trent, we owe you. We owe you for all that. And it's like 40 seconds early and I'm done. I really am in pain. It's part of how I roll right now. But anyway, literally, I'm done. I'm stopping. I'm stopping. We're on slide 38. When we come back next time, we are going to finish, okay? We will finish. And then, Walter, we're going to be officially late on the schedule because we won't get to 6. Well, we'll touch 6. We'll touch it. We'll be at least probably a class period behind. But there's still room in all of that to scoochy it up a little bit. Okay, my friends, I'm done. I'm done with you. I'm just sick and tired. It's really good to be back with you. Honestly, it's really, really great to just be back. And because of y'all's and our opportunities to interact, and you're also funny. And I'm gonna watch Taco Town again because I deserve a break. I deserve a taco. Okay, my friends, I'm gonna shut it down, dial out, and I will see you all on Thursday, or well, you'll see me at least on Thursday, and I'm trying to get back to office hour functionality. Again, sorry for the brutal recovery here. It's been unexpectedly difficult. So, but we're getting there. All right, everybody, take care. See you Thursday. For some of you, I might see you later on this afternoon. Okay, ciao.